Welcome. Today we're diving into the fascinating world of computer memory hierarchy. Have you ever wondered how your computer manages to run multiple programs smoothly, or why some tasks seem to load instantly while others take a bit longer? The answer lies in the way memory is organized and accessed. In this video, we'll explore the different layers of memory in a computer system, understand why this hierarchy exists, and see how it impacts overall performance. By the end, you'll have a clear picture of how computers efficiently store and retrieve data to keep everything running seamlessly. Let's start by understanding why memory hierarchy is so important. Computers process vast amounts of data at incredible speeds, but not all memory is created equal. Some types are lightning fast but expensive and limited in size, while others are slower but can store much more information. By arranging memory in a hierarchy, computers balance speed, cost, and capacity, ensuring that the most frequently used data is accessed quickly while less critical information is stored more economically. This structure is key to efficient computing. Imagine the memory hierarchy as a pyramid. At the very top you have the smallest, fastest, and most expensive memory. As you move down, memory becomes larger, slower, and more affordable. This pyramid structure helps computers decide where to store data based on how often it's needed. The closer a memory type is to the top, the faster the processor can access it. This arrangement ensures that the most critical data is always within easy reach, while less used information is stored further down. The very top of the hierarchy are registers. These are tiny storage locations built directly into the CPU. Registers hold the data and instructions the processor is currently working on. Because they're so close to the CPU, registers are incredibly fast, faster than any other type of memory. However, they're also extremely limited in size, usually just a few bytes. Their speed makes them perfect for temporary storage during calculations and immediate operation. Below the registers, we find cache memory. Cache acts as a high-speed buffer between the CPU and main memory. It stores frequently accessed data and instructions, so the processor doesn't have to wait for slower memory. Modern computers often have multiple levels of cache, L1, L2, and sometimes L3, each with different sizes and speeds. The closer the cache to the CPU, the faster it is, but also smaller and more expensive. This clever design helps keep the CPU running at top speed. Next in the hierarchy is main memory, commonly known as RAM or random access memory. RAM is much larger than cache and registers, but it's also slower. It stores data and programs that are currently in use, allowing the CPU to access them quickly when needed. When you open a new application or load a file, it's loaded into RAM. While not as fast as cache, RAM is essential for multitasking and smooth system performance. Low RAM, we have secondary storage devices like hard drives and solid-state drives, SSDs. These devices store data permanently, even when the computer is turned off. Secondary storage is much larger and more affordable than RAM, but it's also significantly slower. This is where your operating system, applications, and personal files are kept until they're needed. When you launch a program, it's loaded from secondary storage into RAM for faster access. The base of the hierarchy is tertiary storage, which includes devices like magnetic tapes and optical disks. These are mainly used for backups and archiving large amounts of data that aren't needed frequently. Tertiary storage is even slower than secondary storage but offers massive capacity at a low cost. It's ideal for storing data long-term, such as system backups, old records, or large media files that you don't access every day. One of the key trade-offs in memory hierarchy is between access speed and storage capacity. As you move down the hierarchy, memory becomes slower but can hold much more data. Registers and cache are lightning fast but tiny, while secondary and tertiary storage are massive but take longer to access. This balance allows computers to operate efficiently, keeping the most important data close at hand and less used information further away. Cost is another crucial factor in the memory hierarchy. Fast memory like registers and cache is expensive to manufacture, which is why it's only used in small amounts. As you move down the hierarchy, memory becomes cheaper per byte, allowing for larger capacities. This cost-performance balance is why computers use a mix of different memory types, each serving a specific role in the system. CPU, or Central Processing Unit, is at the heart of the memory hierarchy. It interacts directly with registers and cache, fetching instructions and data at incredible speeds. When the CPU needs information that isn't in the cache or registers, it reaches out to RAM or even secondary storage. The efficiency of this process depends on how well the memory hierarchy is managed, impacting everything from application speed to overall system responsiveness. Computers use specific patterns to access memory efficiently. For example, data that's used repeatedly is kept in faster memory, while less frequently used data is stored further down the hierarchy. This approach, known as Locality of Reference, helps minimize delays and keeps the system running smoothly. Understanding these patterns is key to optimizing both hardware and software for better performance. Temporal locality refers to the concept that recently accessed data is likely to be accessed again soon. For example, if a program uses a variable, it's likely to use it again in the near future. By keeping such data in faster memory like cache, computers can speed up repeated operations and reduce the time spent waiting for data to load. Spatial locality is another important concept. It means that data located near recently accessed information is likely to be used soon. For instance, when a program reads a value from memory, it often needs nearby values as well. By loading blocks of data into cache, computers take advantage of spatial locality, further improving performance and reducing memory access times. When the CPU looks for data in the cache and finds it, that's called a cache hit. If the data isn't there, it's a cache miss, and the CPU has to fetch the data from slower memory. The goal is to maximize cache hits and minimize misses, as this keeps the processor working efficiently. Techniques like prefetching and smart cache management help achieve this balance. Virtual memory is a clever technique that allows computers to use part of their secondary storage as if it were additional RAM. When RAM is full, the operating system moves less used data to the hard drive, freeing up space for active programs. This process is invisible to users and helps computers run larger applications than would otherwise fit in physical memory. Paging and swapping are techniques used to manage virtual memory. Paging divides memory into small blocks called pages, which can be moved between RAM and secondary storage as needed. Swapping involves moving entire processes in and out of memory. These methods help computers juggle multiple programs efficiently, even when physical RAM is limited. Memory Management Unit, or MMU, is a special hardware component that handles virtual memory operations. It translates virtual addresses used by programs into physical addresses in RAM. The MMU ensures that each program runs in its own protected space, preventing data corruption and improving system security. The operating system plays a central role in managing the memory hierarchy. It decides which data stays in RAM, which is moved to virtual memory, and how cache is used. The OS also handles memory protection, ensuring that programs don't interfere with each other. Efficient memory management by the OS is crucial for system stability and performance. See how the memory hierarchy works in practice. When you open a program, the CPU first checks the cache for the necessary data. If it's not there, it looks in RAM. If RAM doesn't have it, the data is fetched from secondary storage. This step-by-step process ensures that the most frequently used data is always close to the CPU, speeding up operations and keeping your system responsive. Despite the efficiency of the memory hierarchy, bottlenecks can still occur. If the CPU has to wait too long for data from slower memory, overall performance drops. This is known as the memory bottleneck. Engineers constantly work to minimize these delays by improving cache design, increasing RAM speed, and optimizing software to make better use of available memory. The world of memory is always evolving. New technologies like 3D XPoint and MRAM promise to bridge the gap between speed and capacity, offering faster, more durable storage solutions. These innovations could reshape the memory hierarchy in the future, making computers even more powerful and efficient. Non-volatile memory, such as SSDs and flash drives, retains data even when the power is off. This makes it ideal for secondary and tertiary storage. Unlike RAM, which loses data when the computer shuts down, non-volatile memory ensures your files and programs are safe and ready to use whenever you need them. Volatile memory, like RAM and cache, requires power to retain data. When the computer is turned off, all information stored in volatile memory is lost. This type of memory is used for temporary storage of active data and instructions, providing the speed necessary for smooth computing. Memory hierarchy is essential for multitasking. When you run several programs at once, the operating system juggles data between registers, cache, RAM, and secondary storage. By keeping the most active data in the fastest memory, your computer can switch between tasks smoothly, giving you a seamless user experience. Memory hierarchy isn't just for desktops and laptops. Mobile devices like smartphones and tablets also use a similar structure. They rely on fast cache and RAM for active tasks while using flash storage for apps and files. Efficient memory management is crucial for battery life and performance in these portable devices. Cloud storage adds another layer to the memory hierarchy. While not physically inside your computer, cloud services act as remote secondary or tertiary storage. They allow you to access files from anywhere, but retrieving data from the cloud is much slower than accessing local memory. Still, cloud storage is invaluable for backups and sharing large files. Servers, which power websites and online services, also rely heavily on memory hierarchy. They use large amounts of RAM and fast storage to handle multiple requests simultaneously. Efficient memory management ensures that servers can deliver content quickly to users around the world, maintaining high performance even under heavy loads. Embedded systems, like those in cars or appliances, use a simplified memory hierarchy. These systems often have limited resources, so memory must be carefully managed to ensure reliability and efficiency. Even in these specialized devices, the principles of memory hierarchy help optimize performance. Gaming computers and consoles push the memory hierarchy to its limits. Fast cache and large amounts of RAM are essential for smooth graphics and quick load times. Game data is streamed from secondary storage into RAM, while the most critical instructions are kept in cache and registers. This setup ensures an immersive and responsive gaming experience. Big data applications process enormous amounts of information, making efficient memory hierarchy even more important. Specialized hardware and software are used to manage data flow between fast and slow memory, ensuring that analytics and processing tasks are completed quickly and accurately. Artificial intelligence and machine learning require rapid access to vast amounts of data. Advanced memory hierarchies, including high-speed cache and specialized RAM, are used to keep AI models running efficiently. This allows for real-time decision-making and complex computations that power modern AI applications. Security is a key consideration in memory hierarchy. The operating system and hardware work together to protect sensitive data, ensuring that only authorized programs can access certain memory areas. Features like memory encryption and access controls help safeguard your information from unauthorized access or attacks. Different types of memory consume different amounts of power. Fast memory like cache and RAM uses more energy, while secondary and tertiary storage are more energy efficient. Managing power consumption is especially important in mobile devices and data centers, where battery life and energy costs are critical concerns. Upgrading your computer's memory can have a big impact on performance. Adding more RAM or switching to a faster SSD can speed up data access and reduce bottlenecks. Understanding the memory hierarchy helps you make informed decisions about which upgrades will deliver the best results for your needs. Cloud computing platforms use sophisticated memory hierarchies to deliver services efficiently. Data is cached close to users for fast access, while less used information is stored in large, remote data centers. This approach balances speed and cost, ensuring reliable service for millions of users worldwide. Virtualization allows multiple operating systems to run on a single physical machine. Each virtual machine has its own memory hierarchy, managed by the hypervisor. Efficient memory allocation and sharing are essential for maximizing performance and resource utilization in virtualized environments. Data centers, which power the internet, rely on complex memory hierarchies to handle massive amounts of information. Fast cache and RAM are used for active data, while slower, high-capacity storage holds backups and archives. Efficient memory management is key to delivering fast, reliable services to users everywhere. Edge computing brings data processing closer to where it's needed, reducing delays and improving performance. Devices at the edge use their own memory hierarchy to process information locally before sending data to the cloud. This approach is especially useful for applications like smart cameras and IoT devices. Real-time systems, such as those in medical equipment or industrial controls, require instant access to critical data. Their memory hierarchy is designed for speed and reliability, ensuring that important information is always available when needed. This is vital for safety and precision in real-time applications. Looking ahead, memory hierarchy will continue to evolve. Advances in materials, architecture, and software will lead to faster, more efficient systems. As data demands grow, new solutions will emerge to keep computers running smoothly and efficiently, shaping the future of technology. To sum up, the memory hierarchy is a fundamental concept in computer architecture. By organizing memory into layers based on speed, cost, and capacity, computers achieve the best balance of performance and efficiency. Whether you're using a desktop, smartphone, or cloud service, memory hierarchy plays a crucial role in your digital experience. Remember, the memory hierarchy isn't just about hardware, it's a strategy for managing data efficiently. By understanding how different types of memory work together, you can appreciate the complexity and ingenuity behind modern computing. This knowledge is valuable whether you're a student, professional, or simply curious about technology. Understanding memory hierarchy can help you make better decisions about upgrading your devices, optimizing software, or designing new systems. Whether you're building a gaming PC, managing a server, or developing apps, this knowledge empowers you to get the most out of your technology. Thanks for joining us on this journey through the memory hierarchy in computers. From the fastest registers to massive cloud storage, each layer plays a vital role in keeping your digital world running smoothly. As technology continues to advance, understanding these concepts will help you stay informed and make the most of your devices. Stay curious and keep exploring the amazing world of computing.